In this video, we're going to talk about a special type of Markov chain called a regular Markov chain. These are special because after a lot of trials, something happens to the kth state distribution matrices. So it makes it easier or possible for us to determine sort of the long-term behavior and make predictions for the future. So if we have a Markov chain with transition matrix P, okay, an initial state matrix S0, the entries in SK are the probabilities that you're in the corresponding state after K trials of the process. Okay, so what we want to know is what would happen to this as the number of trials increases. Okay, so we want to know what happens as K gets large. So we're going to think about the behavior of the state matrices Sk and also the transition matrices P to the power K. Okay, so we're going to talk about this with an example. So suppose each day I come to Camosun, I either bike or drive. Okay, if I drive one day, there's an 80% chance I drive again the next day. If I bike one day, there's a 40% chance I bike again the next day. And today I drove. So we want the transition matrix and the initial state matrix. Okay, first of all, the states here are going to be bike, okay, which I'm going to call B, or drive, oops, okay, which we'll call D when we do our labeling. So now it wants the transition matrix. If you want to do the transition diagram first, you definitely can. So if I have B and D, so drive one day, there's a 80% chance I drive again the next day. So D to D is 0.8, which means D to B is 0.2. If I bike one day, there's a 40% chance I bike again the next day. So B to B is 0.4, which means B to D is 0.6. Okay, so that means our transition matrix P, oops, we need an ordering. So I'm going to move that out a bit. So I'm going to put my states in the order DB. DB. So I have to, now I've picked that, I'm stuck with it for the rest of the example. So if I drive, so this first probability here is the probability I drive to drive. Okay, remember, maybe I'll write this. So these ones on the rows are our current states. Okay, and these ones on the columns are the next states. Okay, actually maybe I'm going to write here. So this is going to be the probability of D to D. Okay, and the next one is going to be the probability that I drive one day and then I bike the next day. So down here it's going to be B to D and then B to B. Okay, and all of these are in our diagram or given above. Okay, so you don't have to do the diagram first. So D to D, they said was 0.8, and D to D, D to B has to be 0.2 then. Okay, now B to D is 0.6 because B to B was 0.4. Okay, so that's our transition matrix. The states are in the order DB. Okay, and then they also wanted our initial state matrix. Okay, so that's our S0. So it's a 1 by 2 because we only have two states. And we have to keep the same order. So it's D and then B. Okay, so this first thing is the probability D today. Okay, so on day 1. So it told me that I drove to school. Okay, I know I drove to school. So the probability I drove to school is 1. I definitely did it. It's a certain event, which means that I definitely did not bike. So the probability that I bike to school is 0. Okay, so now what we're going to do is use these to compute the first 5 state distribution matrices. So I want S1 to S5. And then we're going to see if maybe we can guess what S10 might be. So S1 is going to be S0 times P. Okay, so that's going to be 1, 0 times our matrix P, which I'm not going to write out. So when I do this multiplication, I take this row down this column. I'm only going to get the 1 and the 0.8 hitting. Okay, so this is going to be 0.8 and 0.2. I'm going to get the first row there. S2 is going to be S1 times P. Okay, so that's 0.8, 0.2 times P. So I'm going to take this row times this column. So I get 0.8 times 0.8 plus 0.2 times 0.6. Okay, if you do that, you get 0.76. And if you take that row in the second column, you're going to get 0.24. Okay, if we keep going, S3 is S2 times P. So I take my S2 and I multiply by the P matrix. Now if we do this, we're going to get 0.752 and 0.248. Okay, I'm going to write a bit less now. Okay, so S4 is going to be S3 times P. So I take this one that we just got and multiply by P. And if you do that, you're going to get 0.7504 and 0.2496. Okay, if we compute S5, that's the one we just got, S4 times P. And if you compute that, you get 0.75008 and 0.24992. So what appears to be happening with these probabilities? So we started at 0.8 in the first one, 0.76, 0.52, 752, 7504, 75008. If we had to guess, okay, for S10, what do you think you might guess? So if you've taken some calculus, you might notice that these first coordinates seem to be getting closer and closer to 0.75. And these second coordinates seem to be getting closer and closer to 0.25. So it's like their limit is that, if you've done some calculus. So we might guess that it's going to approach those two numbers. Okay, so we might guess that. We don't actually know that that's going to happen. Okay, but that's what we might think because of the trend that's happening. Now, what would happen if we actually get to that state? So suppose for some k, that sk is equal to that 0.75, 0.25 matrix. What if we wanted the next state, sk plus 1? So sk plus 1 would be sk times p. So that's going to be 0.75, 0.25 times our p matrix, which is 0.8, 0.2, and 0.6, 0.4. So if we actually multiply this out, and I'm going to write it out a bit just so that hopefully you believe me. So this row times this column is giving us our first entry, which is going to be 0.75 times 0.8 plus 0.25 times 0.6. And then I want to do that same row, but with the second column to get my entry in the second column. So it's 0.75, 0.2 plus 0.25, 0.4 times 0.4. Now I highly recommend that you compute these if you don't believe me, but what you're going to get is 0.75, 0.25. You're going to get that back. Okay, so that means that if I actually get to this state, that every state after is going to be equal to that same matrix, right? Because anytime I try to move forward, I'm going to end up with the same one. And then that's the one I'm going to use to try and move forward again. I'm going to get the exact same thing. So we're going to get into this loop. Okay, so maybe I'll write that. So if sk happens for some number of steps k, then we will have the same distribution the rest of the process. So if we know that this is going to happen, then it would make it easier to predict what's going to happen in the future, because we know that eventually we're going to definitely get this distribution forever. So this is what we call a stationary matrix, or a steady state matrix. So if you have the state matrix S, so it has entries at little s1, little s2 to little sn, so it's going to be a 1 by n matrix because it's a state matrix, so it has n columns. Okay, then we would call it a stationary matrix or steady state for this Markov chain with transition matrix P if S times P is equal to S. Okay, so what that means is we're going to take S and multiply by P. This should give you the next state distribution matrix. Okay, this whole thing. So if it actually equals S, it means that you get the exact same thing back over and over and over again. Now, because S is a state matrix, we have to have the SI's are bigger than 0 because they're probabilities, and they have to sum to 1, okay, because one of them has to happen. So in our example before, we had stationary matrix S as 0.75, 0.25, because we just checked S times P is actually S back again. So that is an example of a stationary matrix. Now, what you might be wondering is, does every matrix have only one stationary matrix? And if it does, will they always approach it as K gets bigger? And the answer to both of these is no. Okay, not in general. So you could have more than one stationary matrix, you could have no stationary matrices, and you might not approach it, even if you have one or more, okay? But regular Markov chains always do. Okay, maybe I'll write. For regular Markov chains, so that's why we're going to study them. For regular Markov chains, the answer to both is yes. Okay, so there's always one unique stationary matrix, and we always approach it, okay, as the number of states gets bigger. So in the next videos, we will need to know what it means to be a regular Markov chain, so how do we know when a Markov chain is regular, and then how do we find the stationary matrix without guessing? Okay, so you definitely don't want to use that guessing technique that we did earlier. Okay, that was just to show you what was happening. Okay, if you use that guessing technique anywhere in this course, I'm going to give you 0. Okay, you have to find the stationary matrix using the method that we're going to talk about in a later video. Okay, so in the next video, we're going to see when a Markov chain is regular. Okay, so this you need the transition matrix to be regular. So we're going to see how to tell if that happens. Okay, and then in the video after, we're going to learn how to find the stationary matrix. But that's why regular Markov chains are special, because they always approach the stationary matrix, so they make it easier to predict what will happen in the long term. So as the number of stages gets bigger and bigger.